That's something approximating audio. All right. We're here, such as we are, 10:10. There is 0 more seats there. We did it, climbing over one another. We're at 110% of capacity plus a waiting list of about 110. So the fire marshal probably won't come in the next hour. I'm going to jump in. I promise we'll talk about waiting list and logistics and all the rest of that. So I'm David Culler. It's great to be back here. I've been busy playing chair for the last 4 years, so I've seen many of you, but mostly in things like orientation and whatnot. So it's exciting. It's a little overwhelming to see quite so many faces. But I guess that's part of my fault. Let's set stage for 162. It's new for you. It's new for me. I've never taught this class before, which might scare you out of here. Could be. Right. So, perspective, internet. I'd say, we hear about that library in Alexandria and those Romes and aqueducts and whatnot. No. The greatest artifact of human civilization. We could debate that, but amazing, connecting literally 40% of the planet today, instantaneous communication. It would not have been possible without the things you learn at 162. Period. So this is an interesting time for all of you. If I were you, I would be here too. I can't imagine what an exciting time it is to jump into computer science, into operating systems in particular. Let me try a perspective on that. So think for a second about your graduation. The question is, when will we have 3 billion people on the internet? Before or after your commencement? So I've drawn a little history here, starting from the Dark Ages. That would be 1969, when the internet began with 4 nodes. I've introduced roughly the end of pre-recorded history. That would be the Mosaic browser and the search engine. So let's overlay that. This is kind of so the internet basically grew 70% a year since the beginning of internet time, up until the point where it saturated the United States. And of course, that was about the time when the rest of the world took off. Does it matter? Notice, for example, that about the time when we hit 2 billion people, we saw it transforming nations. So, it's been on this course. When I started as chair, we were there. We are here today. 2.8 billion people. And, maybe we've already hit 3. We just don't know yet. We certainly will by the time you folks graduate. So you are here. I'm an old guy. My introduction started there. So one of the first 4 nodes on the internet with UCSB, that was my father's lab. So that was kind of a cool perspective. Engelbart that invented the mouse, I used to play with his kids. So in at least one lifetime, and of course your lifetime starts, about where? Here. Right? So none of you have ever experienced a time when the internet didn't exist. You have lived in the life of the single most important artifact of civilization, and I'm including all those other civilizations out there. So operating systems were at the heart of all of it. It would not exist without. And some of that, every single ECS class would claim, no, it wouldn't exist without computer architecture. It wouldn't exist without circuits. It wouldn't exist without networking. It's all true. But none of that those incredible advances in the underlying hardware and the amazing software that sits and, has created the App Store and whatnot, without the set of support that the operating system does to make all of that available to those incredible body of applications, processing, communication, storage, and the ability to interact. And, here's a little snippet. This is looking at the penetration of Android versus iOS since 2001, and these incredible points where you see this crossover. I mean, you look at the world around you, and it's so dominated by the competition in the operating system space and what it does to enable applications. Okay? It's no accident. So what we're going to focus on here really is the key building blocks that made that happen. Okay, the underlying concepts in operating systems about processes, scheduling, concurrency, address spaces, protection, isolation, security, networking, distributed systems, persistent storage, transactions, consistency, resilience, interfaces to all those devices. That's essentially our syllabus, is the set of concepts that made this incredible thing happen. If BSD hadn't introduced TCP and the rest of it, right? If these things hadn't happened, then chances are the internet would be as big as about, geeks like us in this room. But it's this family of things that have allowed it to take off. So here's a little example. You grab your phone and you go do a search. You hit the search bar right at the top, operating system. So for starters, you pick up your phone and you go browse. What? We used to make telephone calls on a phone, not access the entire world's information and the other 3 billion people on the planet. And in particular, if that thing was still running Symbian or some of those other ridiculous things rather than a real operating system, you would still be using your phone call for telephone calls, right? Not that you open it up and it runs one of 500,000 applications that are interesting. So for starters, there's no question that incredible breakthrough really was because we put a decent operating system on that phone. Okay, great, you hit it. You've got, and notice, there's no disk in there, but it's got storage, it's got communication. It doesn't look anything like a computer, well, except for it is one. And so you hit Google, boom. Google, that's just some text. What does that mean? A host name? So immediately you can go nowhere until the operating system says, that's interesting, there's a name. I wonder. So distributed services, domain name service in particular, a worldwide distributed system that has no purpose other than to take this text, which is supposed to be a host name, and turn it into an IP address that this amazing thing called IP can go route. And so, there's all this stuff that happens behind the background about delegating DNS authorization and so forth to come back and give you an IP address, which then transparently to you could go access, which you do. And, of course, that then squirts across this amazing thing being routed entirely by that IP address, which, how many of you have taken 122 already? Fair number, but not. Of course, you learned one of the most foundational principles in system design, the end-to-end principle, which is immediately violated. Because you don't go to some particular machine inside of Google. You go to this wide variety of edge devices that do load balancing and transparent replication and redundancy and reliability and all these other things so that you can reach into hundreds of thousands of computers transparently behind you, all running the same operating system, more or less. And notice those things have been busy out there crawling the entire web, and the resources for crawling the web could literally shut down anything on the planet if it chose to. So there's all of these careful admissions control to build up a record of essentially every single document out there, go index it, and of course these days reach into the ad server, know everything about you since the moment you were born, so it can give you just the right kind of shoes you want, and so that it can come back and give you an answer to your query. So every single piece of that only exists because of the things we study in here. Okay, So that's part of the answer of why take 162. Operating system design and systems programming. So why should you take 160? Why should so many of you take 162? Actually, we'll talk about that. So some of you will actually go off and design operating systems. How many of you think you might? Yeah, a few. I mean, more and more than ever, people are. I mean, you look at the incredible open source contribution. We are, of course, BSD, Berkeley Software Distribution. We're the primordial home of open source before we had the term. But these days, all sorts of people, just like you, are contributing the technology that makes this thing drive forward. That's an amazing thing, the most distributed source of innovation and creation that ever existed in all of history. So a few, cool. That's great. You don't, that's not... Many of you, probably most of you, will go create other kinds of systems that use the core concepts of operating systems. Whether you build, how many of you think you might go off and build software? How many of you think you might go build hardware? How about both? How about things okay. So whether hardware, software, some combination of the two, the concepts and design patterns you see in here are going to show up at all kinds of different levels. But essentially, all of you will go build other kinds, apps, systems, all sorts of things that use operating systems. And the better you understand what's under the hood, how they're designed, how they're implemented, the better you use it for, which may be why a lot of you are here. Okay, so what am I trying to do today? So a couple of things you'll notice on slide 1. I had a little reading list and homework assignments in the corner. Every single day down here in the lower right corner will be the things that you should have remembered from the syllabus today. I know I've learned as chair, many faculty think that their students are taking one class and it's their entire life and they should remember every single thing. I figure you're doing many things. It's hard to keep track of them all. We'll try to help. Every morning, I'll put that in the bottom. What I want to do is introduce you to operating system design, some of the concepts. I want to introduce you to this incredible instructional team we have. Spend a little time talking about expectations, logistics, and so forth. And time permitting, maybe we'll get a little excited about what are some of the essential challenges and opportunities. Okay? We'll stop for questions. Okay, so I should introduce myself. Graduated here in 1980. I was a math student in this very room. Computer science at the time meant mostly punching cards down in the basement of this building. So I didn't do much of that. I actually ran the numerical library up at LBL. I basically supported myself through college doing computing because I've been around that for a while. I live in Soda Hall in the AMP lab. Literally, maybe. Yeah, you will too. Office hours are here. The thing about the AMP lab is I don't really have an office, and so my office hours are outside. But I'm always around, and I'll always be around before class and after class, so feel free to catch me then. And you can email me at color@almostanything. I guess so. I mentioned I've never taught operating systems before, so I'm learning with you. I'll try not to screw up too badly. I thought I'd share a little bit of my history on building systems. So when I graduated in 1980, my first job was writing the Cray time-sharing system. This was the most exciting supercomputer, came out in 1976 and 1980. Amazing thing, $24 million. It ran at 12.5 nanoseconds. That would be 80 megahertz. How many of you bought a computer this year? Okay, and what clock rate was it? 3.9 gigahertz. Okay, so that would be how many nanoseconds per cycle? A little 60, right? 4 gigahertz means a quarter of a nanosecond, 250 picoseconds. How far does light go in 250 picoseconds? Okay, 260. So foot a nanosecond, right? So every time light moves literally this far, your machine, which you did not pay $24 million for, right, moves the whole state of the world. This was it was a wild experience. I showed up on day one. The operating system was sort of working. It was written in Fortran. My first day was start yourself here in the code you just took an interrupt and work your way around the operating system. Needless to say, there was not a single stretch of documentation. There was stack feet of code. It wasn't in cards. In fact, one of my accomplishments was when we bought the second machine, it was the first supercomputer shipped without a card reader. It was so hard to get that. But you have all seen this. You remember Tron? Not that Tron, the original Tron, with Kirk Douglas when he was still young. So this was my machine. And, so Disney spent there it went, and all these disk drives, right? Disney spent 3 days, set the whole magnetic fusion energy program back about 72 hours so they could film about 10 seconds of that. No, and this was, so you see these things called disks? Those held 30 megabytes. We had 32 of them. And they were doing seismic analysis. And so my job here is I had a debug shot 4 to 5 p.m. twice a week, where I got the machine to myself. I got to install a new operating system and get on the bus back to Berkeley and see an hour later whether it's still running. So it's a kind of rough debugging environment, right? So you have great tools. Went off to graduate school at MIT doing these crazy data flow architectures. Did a little company on the side. We had the first 386 product on the market. We can talk about DOS and how it is that one of my staff went to Microsoft and suddenly Windows actually had protected mode. I spent a variety of time in building what we used to call massively parallel processors. That's the Cray CM5. Back in the 90s, started this project on cluster architectures. You can't read this, but this is clusters of PCs and workstations gobbling up everything that exists in the computer industry, which they did. So that was the Now project. We had little things like Ink2Me, the first massive search engine, which lost the Yahoo contract to Google, and the rest of that is history. Grad students had Startup of the Week. We did the Ninja Jukebox before Napster. We did the Universal Instant Messenger. I mean, it was fun. I shifted gears into building operating systems for little tiny devices embedded in the real world about 15 years ago. Did a little company, Arched Rock, which got acquired by Cisco, is inside of all of those meters that are in your gas and electric meters. These days, I work on crazy operating systems for things like buildings. So it's really kind of refreshing for me to do traditional operating systems, which I've never taught, and it's interesting. We have this amazing team of GSIs, which I'd like to introduce, starting with Vishal, who's our head TA, there he is. You want to stand up and say a word or two? I'm making sure that all these guys have to see all of you and get over the intimidation. And
I'm Vishal, and I've been working this summer setting up all the infrastructure and automators and setting up the projects that are about to be for this semester.
Yeah.
It should be fun. Yeah, so I'm excited.
Yeah, so Vishal has been huge. He TA'd this course last term, took it before that, took the follow-on 194 course, and without him we would not have the course we have, which you may have noticed has moved considerably, let's call it beyond the previous versions of the course. Partly, we're moving it back to more of core operating systems. And we're getting much more core about it. in the sense of some hands-on system programming experience and a much more realistic operating experience. Everything you do in this course, you will do through Git. So you will push every homework, every project. We have, Vaishal and team have built up this auto-grade environment so that we'll move very much in that direction. So Vaishal's been working like crazy, and I love that word, bug-free. Wouldn't that be nice? Homework 0, which is out, gets you started on all of the tools and will give us a chance to debug some of the auto-grading infrastructure before it really matters. Okay? So get out there. Can we have the rest of the team introduce themselves briefly and give a sentence or two? In order, Isaac, go ahead.
Hey guys, I'm Ian. This is my second time doing this class too. And fourth year, undergrad.
Hey.
Hey everyone, I'm Caleb. I'm a fourth year senior. I guess it's redundant. I'm studying EATS. Some of you may know me from my time taking 61B over the past year, and I'm looking forward to this semester. Hope you guys are well. Hey guys, my name's Stanley. This is my first time as a TA, so I'm really excited. I actually got the chance to do some systems work out in industry. So that was really exciting. I'm really happy to be part of this team.
Hi, I'm Kai-Wei Chen. I'm a third-year PhD student here. I TA'd E122 before, and it's my first time TA this class. I'm very excited.
Hey guys, I'm Will. I'm a junior in EATS, and I'm looking forward to taking this class this semester.
Yeah, well, there's no space anywhere.
I'm going to be a fourth year CS major next year, and this is my first time taking this class, so I'm excited to get a chance to speak to all of you. And I actually took this class last semester, but it's changed a lot since then, so. Hi, I'm Arka. I'm a grad student in EATS, advised by David Collar, and this is my first experience here. Hope it will be.
Let me guess, you got here later. So you guys have all had a chance to get a sense of what we're doing this term. You want to share a thought or two on how you think it compares with previous offerings and how you feel about it? I'll put myself on the line here. Yeah. Yeah.
Last semester,
They only trust you.
last semester I took CS 194-2 core, which was probably the hardest class I've ever taken, and I was inspired but then I learned so much. And I'm not making this class anything like that, but
Please.
that experience has shown me that what a really extremely hard operating system class is like. So I took some of the tidbits from there and added to this class, and it should be fun. I also found that learning how to program in C is extremely helpful. We have a systems internship, because I had wanted to do a systems internship, and they expected me to program in C, and I wasn't as comfortable. So this should help you guys.
Yeah, I guarantee you, your coding interview, which almost all of you will get to experience, the things you learn in this class will be invaluable. Okay, so that's our team. Treat them nicely. Your TAs are really invaluable. They're a huge fraction of the course. So all of these folks are teaching section. ARC is teaching 2 sections. Vajal is head TA. They're responsible for a huge fraction of the course infrastructure. It's way harder to put these things together so that they work, so that you can do a reasonably sized piece and learn a lot from it. That's actually quite a bit harder than doing the assignments. But you'll want to get to know them. You'll want to work with them. They'll be essential in guiding your teams. In many ways, they're going to function as your technical supervisor in the term. I'll say a little bit more about that. Okay, so let's spend a few minutes kind of introducing what the heck is an operating system? Where does it come from? What is it? A few of the basic concepts, and then we'll do some more logistics. So definition, a layer of software that provides other software, what we call application software, access to hardware resources. Okay? In particular, a convenient abstraction of those extremely inconvenient hardware devices, protected access, and protected access to all shared resources. It is the basis for security and authentication. Security doesn't happen accidentally. It happens primarily because the operating system provides enforcement and means of communication amongst logical entities. So we've got a little picture. There's the hardware. There's a variety of applications that to some extent are running on the hardware and to some extent are utilizing the projection of that hardware through the much cleaner interface provided by the operating system. Operating system, what a weird word. Well, in the old days, there were these things called operators. Switchboard operators, computer operators. So the operating system, when I started, literally was these folks would go start a job. And that meant starting the job on the machine, loading its input files onto various tape drives, loading tapes on other things so you'd have out. That process of getting all of the resources needed for this thing called a program to run, humans called operators were, which got replaced by operating systems that do a considerably better job far more efficiently and interactively. That's the operator part. System. What makes something a system? Anybody want to volunteer? It's a weird question. I'll ask lots of open-ended questions. What makes something a system? What's the difference between a system, a software system, for example, and the hello world you wrote the first day you walked into 61A? In fact, most of the programs you write that take some input, compute some output, write some files, put a pretty picture. What makes something a system? We have ecosystems. Yeah? Homeostasis. Explain a little more what you mean.
Self-regulation and maintaining of environment.
Okay, good. So this notion that it's actually part of this perpetually running interactive things that's responding to changes, inputs and outputs, keeping it going. That's absolutely a part of what it means to be a system. Other thoughts? Multiple components. Yeah, that's another really important one. Now, of course, every single computer science course you've seen says it's about divide and conquer. So in some sense, we had multiple components there too. We broke something into smaller components. What makes it a system having those multiple components? Okay, so there's kind of a transfer function. You have various inputs and various outputs, and that's true. And of course, that's true for things that are not systems too, like almost every function in some sense has inputs and outputs and programs we write. Can we connect these three ideas that each of the components have various inputs and various outputs? There's multiple of them. We have this notion that it runs forever, homeostasis, yeah. Yes. So in some sense, the most important part of a system is that all of the parts potentially interact with all the other parts. This is what makes operating systems so exciting. It's what makes it hard. That and the fact that often you're working at interfaces that are below the convenient application interfaces that the rest of computer software gets to enjoy. Okay, but in particular, when it's many components that are interacting, you can't necessarily just solve problems in isolation. You can't necessarily even set up the reproducible test case. because the things that are going on have to do with this non-deterministic, time-dependent interaction of all of these parts, some of which are interacting to the outside world. Okay? So in some sense, that's the biggest challenge, is getting to building a systems perspective and getting to where you can think about how do you debug these things? How do you create these things? How do you analyze these things? And if you ever get to do real operating systems in production, it's pretty interesting. You have bugs that show up once a week. Billions of things happen. What was the confluence of particular settings? How do I even reestablish that versus how do I go in and do the paleontology to figure out maybe it was this. So that's an absolutely essential piece, which over the course of the term you'll get more and more of. Okay. The other notion, let's do a couple of the basics. I've said this a few times. In some sense, what the operating system does is extend the hardware to create a kind of virtual machine that's much more convenient. We, unfortunately or fortunately, will increasingly be dealing with that hardware. So we have this notion, there's software, there's hardware. It's hard, it looks like bricks. And there's programs, they look like text. Right? Okay. All right, there's really processor and memory. That's some of the stuff that's down in the hardware. Those are things, that software needs to run on the processor, store things in memory. Okay, we all get that. And then there's all this other stuff that's important too, right? You got to store things, files, objects. You got to communicate. You got to input devices. All this other hardware that you'd like to get convenient, protected access to. Okay, so really, all of that stuff, your program does not access directly. It only accesses it indirectly through the operating system that provides this convenient virtualization of all of these underlying resources. For example, it's not a processor, it's processes. How many? Millions, thousands, whatever, as many processes as you're trying to run programs at a time. PS, anybody know what PS is? Okay, process. You can see so if you're sitting there, we'll talk about whether laptops, when you go home, type PS, see what it says. Type top, type free. Start to see what's going on in your operating system. Okay, it's not storage. It's not memory. It's an address space. Most of what your program accesses doesn't even exist. Unless it needs to, and instantaneously when it exists, it needs. It's not storage, it's files. And it's not a display, it's windows. You can move them around, you can shrink them and growing. It's not networking, it's sockets. It's not bits and packets over a wire. So these are the virtualized representation of these underlying physical resources created by the operating system. That's what allowed the internet to happen. Oh yeah, and threads. We'll talk more and more about that. You cannot buy a machine today with only one processor in it. Well, you can, but it'll be inside your thermostat. Okay, and even there, but we virtualized that for 50 years to large numbers of threads control running on the same processor. Okay, so in some sense, the instruction set architecture that you learned about in 61C is the only piece of the hardware that the process, the executing part of a program, actually sees. Well, let's talk about that. You write some text, you call it a program. This machine doesn't know how to execute that text. You put it through this whole process to produce an executable file. That's closer. The key thing is that in order for that to run, that program has to become some kind of an image in memory with the registers in the processor actually referencing that. In particular, that there's a particular register, the program counter, containing the address of the instruction that you're executing. The job of the operating system is to create that process and manage it. So there's more software inside there that in some sense is running all the time. That's what we're talking about in here. Okay, we could imagine we write this code that knows how to load a program into memory, create a process, and start it up. What happens after that? It goes into an infinite loop. When we're done, throw the computer away, get a new one. So there has to be some way when, something happens, an interrupt, an event, a timer, a keystroke, where actually we can package up the image of that process, put it aside, and switch to the operating system so that our software can now go manage the rest of those resources. And then switch back. That's the notion of a context switch. Of course, once we have that, then we can start, I can run a program. I could run another program. I could run hundreds of thousands of different interacting programs. I can create systems on top of this system, which is the ecosystem that today you all live in. Which means the operating system is now responsible for scheduling those, who runs when, from protecting one from another, from protecting us from all of them, protecting them from us. Talk about some of those things. So that's scheduling, protection, isolation. In effect, the operating system is what creates this protection boundary. And we drew this pretty picture, well, ugly pictures, of all of these things. But in fact, there's all this other hardware that, when your program, process, actually wants to do anything, it's got to access, for example, files on the disk or communicate across the network. It's doing that through the operating system in a protected fashion. In fact, there's all kinds of other hardware down underneath. High-performance buses, lower-performance buses, way lower-performance buses. This is your USB, for example. I/O controllers, bus controllers. There's all these other lower-level pieces of hardware that the operating system has to manage so that you get this comfy world up top that says, open this file, read it, write it, send it across this socket. As part of providing those convenient resources, it also enforces protection. So you can't clobber the hardware and can't clobber each other's access. Okay, and for example, this program doesn't exist out there in the world. It exists over here on the disk too. And so just as your programs have to read and write it, the software called the operating system to be able to transfer that into memory and run it and page it back forth and so forth. So that many of the facilities that we create for the benefit of all those user applications, we actually need ourselves inside the operating system. Okay. That's in a nutshell. Let me tell you a little bit about how we're going to try to run this course. And we won't get to the last part, which is my fire hose of what's changed. So today is intro. We're going to do 3 lectures that try to give you a nutshell of everything we do in the course. And the reason for that is in many of the homeworks and projects, we need you to do I/O files and networking. And many versions of this course, we do concurrency, and then we do files, and then we do networking. And it's not until the end of the course where you can actually do anything. So if you like, this is 61C in 1 week done much better. I used to teach, so, in some sense we'll get you up to speed with, and then what we're going to do is to go into each one of those much more deeply. Into concurrency, threads, thread schedulers, protection, so forth. That's the first project. Into how do we construct an address space. That takes us a little more than a week. We'll go deeply into how file systems are built. We'll extend that to distributed systems, and then we'll have a variety of advanced topics about the cloud, reliability, security, and so forth. Okay? So that's the syllabus in a nutshell, with roughly how many lectures. And part of what happens is that each of these topics kind of build on things that are before. So we'll return to some topics a little bit. Okay? So initially, we'll talk about processes, I/O, network, virtual machines. We'll get deeply into concurrency, scheduling, locking, scalable locks, deadlocks, what can go wrong, what can go right. We'll get into address translation, how you actually build page tables. We'll get into file systems in some detail. How do you construct them? What is naming, caching? How do you make them high performance? How do you make them reliable? Projects 1 and 2 deal largely with the first part of that. Project 3 will focus more on distributed systems. We'll build a distributed key value store. Okay? In the past, this course has used a kind of classic textbook. I have put that as recommended. There is material that is directly used in the course in the latter part that's in this and not in our main textbook. I've made sure that there's 10 or more copies on reserve. If you don't want to buy it, I fully understand. Okay? So, we've shifted to a new book. This is Tom Anderson, who used to be a faculty member here, and Mike Deline, who used to be a graduate student here. He's at UT Austin. It's a much more directly relevant book. Like these guys write code, which those guys probably don't. Okay, so it's a pretty good book. It tends to go much deeper into fewer things, and that's why we've had to borrow some from the other book, and we'll give you some additional readings. But we're going to follow this pretty closely. It's pretty good. It's actually very good. Okay? We'll provide some additional supplements for things that are not covered well in the books. Okay? I think you learn operating systems by doing it, not by reading about it. So we're going to do 3 projects instead of 4. Okay? They're roughly similar to the projects last year, which finally got debugged down into something that students could really do. The main difference is that the first 2 are done in Pintos rather than in Nachos, which means it's in C. Came out of Stanford. Osterhout used to be here, went there. Okay, so, if the Stanford folks can do it, the Berkeley folks can do it. We will rise to this. Actually, it's a real issue that many of you coming out now as the lower division gets more higher level and whatnot, I'm amazed how many people at Google and VMware and Facebook. No, I need people that can also hack. So you will get good at C. We'll help you. How many of you think you're good at C? That's more than I expected. A few more of you probably are too. That is okay. So the other thing I've done is to bring individual homework assignments. So the projects are done in groups. That's great. We'll talk more. But you also have things that you do yourself. And part of that is to build your experience with C and with the tools. But part of it is it gives you the systems programming side of it. So we'll go build a shell. The thing you open up, okay, it's terminal on Mac OS, it's command.exe on your, right? The sort of basic, how did operating systems project themselves? You'll go build one of those. We'll build a web server. We'll build a variety of things so that you can also understand why it is you care about the things that we're doing inside the operating system. Okay. The model for projects is not terribly different other than I didn't think 5 worked. So we're going to try to do projects of 4. We're not insisting you be in the same section. That's a logistical nightmare. It's wonderful if you are. Getting 5 people in the same section is impossible, and they take turns doing the work, so most of them don't learn most of the project. So we hope you'll really work together. And part of it is to give you a lot more of the kind of experience you'll have as you leave here and are engaged in doing systems work in a variety of places. So in some sense, your TA is your Scrum Master. ask them. That they're going to be each managing, so 30 students per section, 4 students per project. Okay, so they're going to be managing, on order 8 teams. Okay, and that's the relationship that they'll have. Grading breaks down more or less like this. We've got 3 midterms, 3 projects, essentially midterm every 5 weeks. We're going to do homeworks, essentially the same as a project. Participation, we really hope you engage. And we've tried to structure the project. We'll talk a little more about how exactly the projects are managed. But part of the point is it's not just passing the tests. That's an important part of it. But it's also the design work you do in getting there and the quality of code that you produce coming out of it. Everything you do will be through Git. So we'll move you into the open source world. You will submit your project by pushing to the release branch, which will trigger the auto grader, which will send you a wonderful piece of email that tells you got all the tests right, hopefully. We're actually going to structure it so that you will push more than once, because your TAs want to know how you're doing, not just whether you magically got it to work at the last minute, 2 seconds before the deadline. They want to see your progress along the way, like you would if you were working in a team. They'll be reviewing your code as you're building it, and we can do that all. We'll tell you about that. Okay, so how do you get started? The answer is homework 0. All good numbering systems start with 0. Is how you get started. It's got everything. It's incredibly long. Started yesterday. Some of you did. It walks you through all the tools. No, we're not going to give you pieces of paper with your account on them. Vaishal's written all these scripts to integrate that. You'll get a GitHub account. Do you want to say a word or two more about that?
Yeah, sure. All of you should create a GitHub account if you don't already have one, and then...
So let's check. Who has a GitHub account already? Yeah!
Good. So part of Homework 0 has a link to a Google form, and you fill out that Google form. Even if you filled it out yesterday, you'll have to refill it out because I wiped all the responses. I didn't expect people to start early, like before school. Anyway, and then you'll get an email with your account form, and you'll get another email from GitHub saying you've been added to the CS162 organization, and you'll get a private repo called whatever your account name is. So if your account name is AB, you'll get a private repo called AB, and all your homework will go there. And later on, when you create a group, you'll get a private repo for your group called Group X, where X is your group number.
Great. So everything you care about is explained in Homework 0 beautifully. Go to section next week, not yesterday, next week. In fact, go to section every week. In previous, they've done these little quizzes to penalize you if you don't go to section. I promise I'll finish on time. I got 2 minutes. Wait list. So currently there's 110 people on the wait list. We are going to be at 110% of this room. We're not going to take on another 100 people. However, we're going to do everything we can to service as much of the wait list as we can within those constraints. We will service the wait list at least weekly. So if you can go ahead and pull Homework 0. You can go ahead and get an account. You can get started. The place where things will change is only registered students will start the first project 4 weeks from now. Okay? So you can get started. You can do Homework 0 and 1, even 2. Okay? But also, those of you that are in the class and think maybe this semester is not for you, please, if you want to drop, then we can get people on the wait list into the class as soon as possible. We'd like to do that. Thank you all. We'll see you on Wednesday.